Okay, so I'm here today to talk to you about a new method for filling in missing values in messy data tables called generalized low-rank models. This is largely work from my PhD thesis at Stanford, which I did with my advisor, Stephen Boyd. This is also joint with Angie here at H2O and two other collaborators at Stanford, Corinne and Reza. So right now I'm at the Center for the Mathematics of Information at Caltech, and I'll be moving to Cornell this summer. Okay, so here's the data model that we start with. We imagine that someone has come to us and given us this messy table of data. And what did it have in it? Well, there seems to be one row for every for each person. Maybe we have, here I'm showing 4 people, but maybe we have thousands, tens of thousands, millions of people. And here I'm showing a couple of things that I know about them. So I know their age, I know what gender they are, I know what state they're in. And these are, what are these data types, right? Okay, so age is, I guess, an integer. It takes on integer values usually. Gender is a Boolean. State is a categorical variable. It takes on one of 50 different values. Income is a real number. Education is an ordinal variable. A high school is less than college, is less than a master's degree. And we just want to understand what's going on with this data set. Who are these people? For example, can we group them into some sort of reasonable demographic groups? Can we figure out who's similar to each other? Can we find a typical response within these demographic groups? Can we fill in the missing entries? Could we figure out, for example, what the age of this male in California who makes $102,000 a year is? These are sort of typical things that we might want to do just to understand what's going on here. So because I'm a mathematician, my first instinct is to generalize the problem. Okay, so here's the problem setting we'll be working in. We're supposing we've got a data table that has m examples in it, so these are the rows, and n features. These are things that we know about these examples. So the examples might be things like patients in a hospital. They could be respondents to a questionnaire or survey. They could be households in the United States. They could be assets in a financial model. And the things we know about them might be their answers on tests, their responses to questions, maybe sensor measurements, or responses that each of a number of times. So we're always going to think about the ith row of this data table as giving the feature vector for the ith example, and the jth column as giving the jth feature across all the examples. And so if we're going to do things like filling in missing data, we're going to need to impose some structure. We're going to need to suppose that we know something in addition about what's going on in this data table. And the kind of structure we'll be looking at is low-rank structure. So we're going to suppose that we can approximate this data table as the outer product of 2 numerical matrices. So we're going to have a skinny matrix X that has 1 row for every example in our data set, and a fat matrix Y that has 1 column for every column in our data set. And we're going to hope that X times Y is approximately equal to A. Okay? Now, this doesn't quite make sense yet because A is a data table that has weird heterogeneous values in it and a lot of missing values, and X and Y are both numerical matrices. Okay? So the main thing that I'm going to have to explain to you is what we could possibly mean by saying that this numerical low-rank matrix, X times Y, is approximately equal to this data table A. Okay? But if we could do this, we would be really happy. Why would we be happy? Because we'd have 1 numerical vector for every row of our data set, and we'd have 1 numerical vector, short numerical vector, for every column of our data set. So that means that we'd have, in some sense, this vector representation for every example. So before we had this crazy set of feature values, a lot of them were missing for every example, and by performing this approximation procedure, we get a short vector, right? And vectors, right? Machine learning algorithms love vectors, right? So anything else you want to predict, you can take these vectors rather than taking the original messy data. So you can use them in any subsequent analysis you want to do. You can think about these vectors as being sort of a compressed representation for every example, and the vectors Y as being a compressed representation for every feature. You can also fill in missing data by looking at these inner products between the rows xi and the columns yj. So here, the xi's are always row vectors, yj's are always column vectors, so xi, yj is a number. Okay? So why would we use this kind of low-rank model? Why would we want this? Well, I've already said a couple of reasons. One is that the space required to represent the model is much lower than the space required to represent the original data table. So it reduces the storage space. Another reason might be to understand the data table better. You could visualize these short vector representations, or you could cluster them to find similar examples or similar features. A third reason might be to remove noise. You can figure out which entries in your data table are not well approximated by xi times yj. And those are either, you can think of them as noise, or you can think of them as outliers and entries that you might want to investigate further. The third reason would be to infer missing data, because every entry in this matrix xi times yj is populated, whereas you had a lot of question marks in your original data table. And the last reason is to simplify data processing, because you can use these vector representations in subsequent analysis. Okay, so let's talk about a simple case that you've probably mostly heard of, and that's principal components analysis. So if this data table were actually a matrix full of real numbers, so A is now a matrix full of real numbers, then a good low-rank approximation for that matrix is given by principal components analysis. So we say, why don't we find a matrix x times y that minimizes the distance from A in the sense of squared error? Okay? This is a super old problem. This was first proposed by Carl Pearson in 1901 and named by Hoteling in 1933. And one of the reasons that they really liked it is because there's an analytical solution. If you count computing eigenvectors as being analytical. So here's what you do. You just compute you compute the SVD of your data matrix, U sigma V transpose, and then you can write down a solution x and y in terms of that SVD. It's not unique, but sort of any solution of this form is a solution. So they loved that because they could compute it in like 3 lines, and indeed, like sometimes they show the entire computation in their paper. It's crazy. But we know today that there's another way to do it, and there's a way that generalizes a lot better. And that's alternating minimization. It goes like this. You could fix y and minimize over x, fix x, minimize over y, rinse and repeat. This actually can be proven to converge to the same value as the SVD, as long as you're not extremely unlucky in how you choose your initial y. So in practice, alternating minimization works, goes to the same solution, and it'll generalize much better. But first, I want to give you an impression for what kind of thing can we do with this low-rank model? How can we interpret it? And for that, I want to go to a very concrete data set. And this is a gait analysis data set. Anji gave a cool demo about using this data set on Monday that you can look at here. So here's how the data set works. We've got, at every time, we have a measurement of each of a number of parts of someone's body. Okay, so we know the location of each of their body parts at each time. And they're walking forward in time. And what is a low-rank model of this going to look like? Well, we're going to have rows of, I'd like to be able to, so we're going to break this up into one row of x for every time and one column of y for every body part. You can think of the rows of y as actually they're going to have a number for every body part in every position, so that's going to give you a stance. And the rows of x are going to tell you how much of each stance is present in the person's posture at any given time. Okay, so let's see what this looks like. So the columns of A just look like, for example, these are the y coordinates over time. So you can see the head is bobbing up and down a little bit. The feet are moving more wildly. Here's the z coordinate over time. That's forward and back motion. So you can see the legs are swinging with a large amplitude. The arms are swinging with less large of an amplitude. And now we're going to fit our low-rank model to this. And what do we get out? Here's one row of y, just plotted with the sort of y and z coordinates. And you can see it looks kind of like a person. There's the top of the head. Their right foot is back. Their left foot is forward. Cool. And then you can see in the columns of x how the importance of each of these these principal stances in the person's posture is varying over time. So you can see it looks like sort of quasi-periodic, but this is definitely not, just a bunch of sine waves of different frequencies. So you can see sort of how the different stances alternate over time. Now, the other thing that I really like about this model is we can actually use it to denoise the original data set. So here I've plotted a column of A in blue, and you can see it has a lot of sort of funky wiggles in it. And then I've plotted a column of our imputed values for this sensor measurement in red. And you can see that that curve is much more smooth. So if you show this to someone in a gait analysis lab who does motion analysis all day, they say, oh yeah, those weird wiggles on the blue curve, that's sensor noise. That's just junk. Actually, I think that the red line is closer to what really happened, the way the person really moved. And the reason why the low-rank model gets it right and doesn't pick up on the noise is because it can't simultaneously represent the motion of every part of the body and represent the sensor noise. Because the sensor noise is only in one sensor as opposed to sort of a global property of the motion. Okay, so it's picking up on global properties. It's getting rid of sort of local noise. Okay. But we want to be able to use this for crazy heterogeneous data like a sort of a data table that someone just comes and gives to us. And in order to do that, we're going to need to generalize principal components analysis in 3 ways. So the first way is we didn't observe every entry in this data table. So instead of minimizing over every entry in the data table, we're only going to minimize over the ones that we saw. So for us, that's going to be this index set, ij in omega. The second thing we're going to do is we're going to generalize the loss function. Before we were using squared error, we said we wanted xi times yj to be close to aij in the sense of squared error. Now we're going to say, no, I just have some loss function that tells me how angry I am to have approximated this entry in the data table aij by this real number xi times yj. The third generalization is we're going to add some regularization. So we're going to say, please make me a model in which xi is small in the sense of ri and yj is small in the sense of rj. And we can use that to impose structure on the model. We'll see a number of ways to do that. Okay, so here's the first sort of simple example where you might want to do this. Suppose you've got a table of numbers, except some of them are missing. Okay, now I've seen a lot of people, when presented with data of this type, say, well, I don't know what to do about the missing data, so I guess I'll just take the rows that have any missing entries and throw them out. Okay, we don't like throwing out data. That's a waste. So instead of throwing out your data, you can actually draw strength from the entries that aren't missing by just minimizing over the entries you saw and not the entries you didn't see. Okay, there's a second setting in which this is extremely important, and that's a setting in which you've observed almost no entries. So you might think about the Netflix, the famous sort of Netflix prize problem. Most people have not rated most movies. So if you took the people by movies rating matrix and threw out all the rows that had any missing entries, you would throw out every row. So by using this matrix completion paradigm, you can still fit a good model of that data that predicts well what ratings people are going to give. And this regularization is quite important for allowing statistical generalization in that setting. Okay, so in general, how might you pick your losses and regularizers? Well, the regularizers are usually chosen to impose structure on the data. So if you want some sort of good statistical properties, in the same way that you might use rigged regularization when you're running a regression problem, you might use an equivalent of regularization in a generalized low-rank model. So you might use a quadratic regularizer on both x and y. If you might want a sparse model, because sparse models are sometimes easier to interpret. You can use L1 regularization to encourage sparsity in your model, so they're not sort of too many archetypes that are present for any given example. You might be interested in a non-negative model. Sometimes you want to interpret your coefficients as being positive things like energy, in which case it's important that they be non-negative to allow the interpretation to go through. It's easy to enforce that. You could say, I'm going to say that my regularizer is infinite if x is negative, and it's going to be 0 otherwise. So that's this indicator function is infinite when its argument is not satisfied. You might also ask your model to be clustered. So you could say, I want exactly one entry of x to be 1 and all the rest of them to be 0. That ends up saying that for any given example, exactly one archetype is activated. No other archetypes are activated. Okay, so it may sound sort of weird, but it turns out if you just write down this model with a quadratic loss, and you think about what alternating minimization on that model does, you'll get the exact same algorithm as the standard k-means algorithm. where you iteratively assign points to clusters and then move the cluster centroid to be the center of the points. So this should tell you that the generalized low-rank models, this alternating minimization procedure, is actually something you're quite familiar with from contexts like k-means. Okay, so what about loss functions? So for real data, the one that you've seen before is the squared error loss function. But you might also try other robust losses, like the absolute value loss function or the Huber loss function, which is quadratic for small values of its argument and linear for large values. This means it's less sensitive to outliers. The quadratic function... Okay. What about for Boolean data? Well, there's sort of standard loss functions that you can use for Boolean data. So, some of my favorites are the hinge function, hinge loss, and the logistic loss. So in this way, you can keep just going through the machine learning literature, take your favorite loss function for your new data type, and you can plug it into this bilinear context. Right? So take anything that you know and love from a regression context, plug it in here, and you have a loss function that you can use in this unsupervised sort of bilinear setting. So there are sort of standard loss functions for count data, for ordinal data, and for categorical data that I'm not going to go into here. And so by sort of mixing and matching these loss functions and regularizers, you can create a large fraction of the machine learning literature by choosing them appropriately. So we already talked about matrix completion. You can get non-negative matrix factorization just by choosing a non-negative regularizer. Sparse PCA is the name that's often given to this L1 regularized generalized low-rank model. You can get sparse coding, you can get k-means, robust PCA, logistic PCA, Boolean PCA. Okay, so the whole menagerie is here. And I think it's quite useful to think about it in the context of a generalized low-rank model because it helps you, it gives you a framework to hang all of these models on, right? So you don't need to remember sort of individual ones. You're like, oh yeah, well I've got sort of Boolean observations. Of course, I should use a Boolean loss function. Okay, so let's see what this model can do. Here's a synthetic data set that I've generated to be low rank. And the first chunk of columns all have real valued observations. The second chunk of columns, I've truncated them into Boolean observations, 0, 1. And the third chunk of columns, I've got observations with values between 1 and 7. Now I remove the second two types of columns, the observations for those two types of columns, for about half of the rows. This is like saying I administered the SAT to a bunch of kids, except I lost the results of like the math section and the essay section for half of them. Do I have to make them retake the test? And the answer is, if I were using PCA, I might, because you can see that the error, this yellow part, is actually very high when I reconstruct using PCA. But if I use a loss function that's adapted to the kind of data, so I use a Huber loss function for the real values, hinge loss for the Booleans, and an ordinal hinge loss for the ordinals, then I can actually recover with extremely low error. So no, the kids do not need to retake the SAT. Machine learning comes to the rescue. Okay. Now, if you're going to apply this model in practice, it's very important to know how to choose the parameters. The most important parameter in these low-rank models is how do you choose the rank that you're going to allow. And there's an easy way to do this. So because the model can deal with missing data, it's easy to cross-validate the model. You say, I will leave out more of the entries that I've observed. I'm going to fit a model with whatever parameters I want and see how well it fits on the entries that I've left out. So here's an example showing how to choose the rank and also the rank k, and also the strength of the regularization gamma. So in this particular plot, you can see that k equals 1 fits very badly, k equals 2 fits, I guess, twice as well, and k equals 3 through 5 all fit quite well. So in other words, it's identifying the fact that you need at least sort of 3 rank components to represent this model. And it gets it right because I actually synthetically generated this data to have rank 3. Good. Okay, so now how about some real data? Here's some data from the American Community Survey. This is a subset of census data that they administer to 1% of the American population every year. And they ask them a bunch of economic and demographic survey questions. These are things like, their income, how much do they pay in utilities, how many weeks do they work per year, how many hours do they work per week, what's their level of education, right? So it's all sorts of things. And you can imagine that some people don't feel comfortable sharing this stuff, and so a third of the responses are missing, or they're lazy. Not clear. Okay. Now, if we just wanted to understand the population of the United States, who are these people? We might fit a low-rank model to this data set. And what could we do with that low-rank model? Well, we might want to cluster the respondents on this data set, finding demographic groups. And that's very easy to do now because we've got a numerical vector for every person in the survey. We can just cluster those numerical vectors. We can find demographic profiles by looking at the rows of Y in this low-rank model. We can identify which features are similar, which of these questions on the survey are redundant with each other, just by looking at which columns of Y are close to each other in Euclidean distance, right? These are vectors. And we can impute missing entries by just minimizing the loss function over its second argument to find the most likely value that would have been generated by that parameter. Okay. So how do we do this? Well, there's sort of a standard way based on what I've told you, right? We can use a sort of a loss function for each data type that's adapted to that data type. We can scale the losses in regularizers to reflect what we think is important about the data set, and we fit the model. And here's what we get. Here are the most similar features in demography space. We can see Alaska is like Montana and North Dakota in demography space. It kind of makes sense. California is like Illinois in the cost of water. Okay, which, if you've been following the drought, makes sense. I like this. Hours worked per week is very similar to weeks worked per year in your level of education. I always tell grad students that maybe they've made a bad choice when they see this. Okay. Here's a really interesting application of low-rank models. Suppose that I want to predict something. I've got a data set, and I really want to predict something in this data set, but it has a really large categorical variable. I want to be able to make use of this variable, but I don't want to overfit. So here's an example. Here, I'm showing data from the US Wage and Hour Division, and these are violations of labor laws that have occurred. So here, I'm only showing companies that haven't violated labor laws, because I thought it would be too sensitive to show you companies that had. Okay, so H2O, Stanford, and Caltech are doing pretty well. They've got 0 violations. But there are a bunch of companies that have violated these labor laws, and we want to figure out which ones are likely to violate the labor laws. Okay, so this has a bunch of different columns, about 250 columns, but in particular it has zip code in it, okay? And zip codes, there's 33,000 or so zip codes in the United States. Most of these zip codes only appear once in this data set. How can we use zip code at all in figuring out the likelihood of violation, right? Maybe it does depend on geography or something about the zip code. Okay, but if we just fit this naively, right, we've only got 200,000 rows, we've got 33,000 zip codes, and most of them only appear once, we're going to massively overfit if we build a separate model for every zip code. So we want to do something else, and here's what we can do. We can take another data set in which zip code appears, and we can fit a low-rank model to this new data set. Okay, so what do we do when we get this? We get a short vector representation of every zip code. Okay, and here I'm just using some demographic data. So I know something about the demographics of the zip codes. I'm embedding the zip codes in some kind of demographic space. Okay, what does that look like? Well, here I'm plotting just a couple of the zip codes. So you can see Cupertino and Sunnyvale are very close together in demographic space. They're very far away from McCune, Kansas, which is a place that you've probably never heard of, and that explains why it's far away from these other ones in demographic space. And then sort of up in the other corner, we have East Harlem, which is sort of the opposite side of this demographic space. Okay. Now, the test of whether this is a good embedding, this is a good representation of the zip codes, is whether or not it does a good job helping us predict these labor violations that we were interested in. Okay? So we're going to try out 3 different tests. The first is we're going to expand zip codes into a categorical variable. So this is fitting an offset, basically, for every zip code in this model. The second is we can just concatenate these 2 tables. We can just join them on the zip code. So we're appending all the demographic features, this huge thing, into our labor violations data set, and using sort of all those features to predict. And the third version is this low-rank model. So we take the zip codes, we embed them into this low-dimensional space, and we append that low-dimensional representation to the labor violations data set. Okay. And we're going to see how well they do on this supervised task. So you can see that this turning the zip code into a categorical gives a I'm pretty interested in the test error, right? How well it does on the prediction task. So it gives a test error of 0.22. Concatenating both of them actually does a pretty bad job, 0.25. And using this low-rank representation does the best job of all, 0.19. Okay? So somehow this low-rank representation of zip codes is finding the right representation in demographic space. You can also see a tremendous improvement in runtime compared to the categorical version, which is using 32,000, adding 32,000 variables. The low-rank model is adding 10. Okay, so it does much better. Now I want to say a couple of things about the algorithm. I told you about this idea of alternating minimization: fix y, minimize over x; fix x, minimize over y. If the loss functions and regularizers are all convex, which all the ones I've told you about are, then these are convex subproblems, and they're all very small because they actually decouple over x and decouple over y, so you can perform them in parallel. You can show that the objective converges as long as the losses and regularizers are bounded below, and it usually finds a very good model in practice. The other thing is that it's naturally parallel, so it naturally scales to huge problems, which is why we've implemented this in H2O. But alternating minimization doesn't necessarily make sense because it might take you a long time to minimize over x even when you have a pretty bad estimate for y. So one thing that you can do instead is you can just do a simple update at every step. Rather than doing a full minimization, you can just take sort of one step in the right direction. My favorite way of taking the step is using the proximal gradient method, which is what's implemented in H2O, where you say I'm going to take the gradient with respect to the loss function of, in this case, xi, and then I'm going to take a proximal step with respect to the regularizer. What's nice about this is it allows you to enforce both hard and soft constraints. So we have hard constraints like the representations xi should be non-negative, and soft ones like they should be small. And all of them are very easy and fast to implement. And the total time per iteration is basically sort of less, it's the same order of magnitude as one iteration of eigenvector decomposition. So it's sort of on the same scale as PCA. So we've got a bunch of implementations. The one we're showcasing here is the H2O one, of course. But sort of we have a number of different languages. Okay, so with that, I'm going to conclude with a tiny bit of time for questions. We've seen how to use generalized low-rank models here to find structure in data automatically, to handle huge and heterogeneous data sets in a coherent way, and to transform big and messy data sets into small and clean data sets that we can use in subsequent analysis. So thanks very much, and I'm happy to take questions.
I told you guys that was going to be great. Questions? We got a time for just a few.
Hi. Yeah. So I was wondering, regarding the components or the archetypes, is there some systematic way to understand what they mean? So like you can kind of label the clusters and present that to like business users?
Yeah. So I think that the simplest way to understand what they mean is to take the archetypes and then put them back into the feature space. So once you put an archetype back into feature space, and that's sort of by doing data imputation with respect to the archetype, so minimizing over the sort of second argument of the loss function rather than the first, you end up with something that looks like just another row in your data set. So you can look at that row and you can say, oh, look, this is, this archetype is like, closest to being a person, a male in New York with such and so an income and whatever. So that's something that I think end users might find very easy to understand.
Hi, I wanted to ask about how you feel that GLRMs would do for the case where you have missing data, but the missing data is significant. So meaning, let's say a doctor is giving a test to a patient.
Yeah. So the fact that the data is missing is itself significant.
Yes.
So in that case, I would actually call that not a missing data. I wouldn't think of that data as missing data. I would think that you have observed the value missing. Okay? So in other words, you've got this like a Boolean indicator variable that's missing or not missing, and you could fit like a hinge loss to that missing or not missing indicator. I think that's probably going to perform much better in that setting than saying it's missing, because the missingness is really informative, and you want to fit that missingness.
Okay, thanks. So I have a question, very basic linear algebra type question. So let's say the rank of your data table A is several orders of magnitude smaller than your number of rows or number of columns. Is there an issue with this method, or is there some numerical stability?
No, that's the best case for this model, right? If the rank is very small, then it means that the algorithm has a complexity that depends on the rank. So small rank means faster runtime. The representations are smaller if the rank is smaller. Everything gets better if the rank is smaller.
Great, thanks.
Yeah.
Okay, this guy's been real patient with his arm up. We'll get one more. Just run back there, Navdeep.
Thanks. I was just wondering about normalization and standardization of data.
That's an excellent question. That was the one slide that I wanted to add and didn't have time for. So there's a really simple generalization of the standard normalization standardization procedure for PCA to a generalized low-rank setting. If you think about, so in PCA, the way that you normalize and standardize is you subtract off the mean of every column and divide by the variance. In this generalized context, the mean is just like the argmin of the loss functions in any column. So if you had quadratic loss, argmin of that is the mean. If you have some other kind of loss, it's something else. For L1 loss, for example, it's the median. So in that way, you can generalize the mean. And then the variance is just the average of that loss function on the data evaluated at that sort of mean parameter. So you can sort of include this offset by the mean and dividing by the variance by modifying the loss functions rather than the data. So there's a nice way of doing this without performing any arithmetic on the data. And that standardization is sort of a default option that you can just turn on in H2O.
Okay, great. Can we get a round of applause for our speaker?
Thank you.